Right. Good luck.
So, good afternoon, good morning, good evening, dear friends, dear colleagues. So we have in Vienna today, or we had 25,000 new infections, yeah? Which also means that so we are still very much in the pandemic. And this also means for us that the OWOS seminar will continue. And so we planned fantastic talks for the next weeks. And we have today a great talk given by Pontus Giselsson from Lund University in Sweden. So Pontus received his PhD from Lund in 2012, sorry, and then he moved to Stanford University on a postdoctoral position. Then he went back to Sweden. He learned a lot of great things in the United States, in the group of Stephen Boyd. Pontus is working on very cool topics in optimization, in operator splitting. He's very much interested in applications, in machine learning, in signal processing, in applications coming from engineering. So we are looking forward to a great talk today. Pontus, you have 45 minutes for a presentation. So please share your tablet.
Yes. Thank you very much for the introduction. Let me just share my slides. Yes. So again, thank you for the introduction and thank you for inviting me for giving this talk. So what I would like to present is our work on nonlinear forward-backward splitting with projection or momentum correction. And this is joint work with my PhD student, Martin Morin, and my postdoc, Sebastian Bannert, who has been with Radu before. So essentially, what I will present is an algorithmic framework for algorithms that solve monotone occlusions. And this framework has many of existing operator splitting methods as special cases. And it's also quite easy to devise new methods based on this framework. So, but what we will start with is the proximal point algorithm that I think all of you know. So we consider the problem of finding point X in the Hilbert space, real Hilbert space H, such that 0 is in AX, and we assume that A is maximally monotone. And one algorithm to solve this that I think all of you know is the proximal point algorithm, PPA. And this works potentially with the relaxation, but it iterates the resolvent of A. And we denote the resolvent by J here. And we have a step size gamma K, which is upper bounded and uniformly bounded away from 0 as well. So this is our step size parameter in the algorithm. And this algorithm may be more seen like a conceptual algorithm. So if you have a monotone inclusion problem, as I just stated, maybe we cannot directly typically apply the proximal point algorithm because it might be as expensive to take one step of the algorithm as to solve the original problem. But if we do clever choices of, for instance, this page where we apply the algorithm or the operator A, we can get very important special cases of PPA. So for instance, the Chambolt-Pock method can be seen as an instance of the proximal point algorithm, and also Douglas-Ratchford splitting and its dual variant AGMM if we use dual step size 1. All can be seen as special cases of the proximal point algorithm. So what this algorithm provides is a unified convergence analysis for all its special cases. And the convergence analysis, if we assume that A is maximally monotone, is essentially that the resolvent that we have has full domain by Minty's theorem. So the algorithm is well defined for all inputs. And then it's quite easy to show as well that this operator is Fermi non-expansive, which gives single valuedness, and it can be used to show convergence, weak convergence towards the solution. And typically it can be easier to show convergence of an algorithm by showing that it is an instance of the proximal point algorithm and show this type of convergence, then directly trying to prove convergence for the special case. And in an extension of the proximal point algorithm, we can add a co-cursive operator to the problem formulation. So we now consider a problem of finding an x in the same Hilbert space H, so that 0 is in AX plus CX. And this algorithm can be solved by forward-backward splitting. We take first a backward step on the co-cursive operator C, and then we take a resolvent step for A. So if C equals 0, we get back the proximal point algorithm. The algorithm analysis for this one is essentially similar to the proximal point method. And the composition here can be shown to be averaged under suitable step size restrictions. And we get a few other special cases of this algorithm, the proximal gradient method and the primal dual method by Condat and Wu. Yeah, so we have seen a few algorithms that are well known and used a lot and that are special instances of forward-backward splitting, but there are also many other operator splitting methods that are not necessarily special cases of the standard forward-backward splitting method. So for instance, we have Tseng's forward-backward splitting method, and we have an extension of that by Briseno Arias and Damek-Davis that includes a co-cursive term, and it's called forward-backward half-forward splitting because the co-cursive term is only evaluated once. That's why the half in the second forward. There is the algorithm by Solodov and Tseng. It's a projection type method for variational inequalities. We have a synchronous projective splitting method that's been analyzed, for instance, by Combet and Eckstein in a more general setting than the synchronous setting, but we consider the synchronous version here. We have the method by Latafat and Patrinos, asymmetric forward-backward adjoint splitting, also called AFBA. We also have methods by Briseno Arias and Combet that uses a monotone plus skew model for solving primal dual problems. The proximal alternating predictor corrector method by Drury, Sabach-de-Boule. We have primal dual methods by He Yuan. And then we have Malitsky-Tam methods that essentially is a variation of the forward-backward-forward splitting by Tseng, where they avoid a second application of one operator to get cheaper updates. And we also have the forward Douglas-Ratchford forward method by Ryu and Wu, number 10 here, and potentially more. So the question that we ask here in this research and in the talk that I have today is does there exist a unifying framework for the methods that we have listed here and also the previous methods, so forward-backward splitting? Yeah, so that's the question that we ask in this talk. And of course, since I asked the question in the presentation, the answer is yes, such a framework exists. And I will present this here. And the framework will be based on two things. So the first thing is a nonlinear forward-backward map that I will introduce right after this. And it has a special case, which is that we call a nonlinear resolvent. And nonlinear resolvent has also been introduced under the name of warp resolvent by Buie and Combet. And these two concepts and algorithms were introduced essentially at the same time. And then it has also, this mapping has also previously been analyzed and discussed by Bauschke, Wang, and Yao under the name of F resolvent. So that's one ingredient. And then the second ingredient is to have some type of correction, because it does not converge by itself necessarily. And the correction is either in the projection correction, or it's a momentum correction. And we will go into these things later. But the general problem that it solves is the same problem as for standard forward-backward splitting. So we have a monotone occlusion problem, 0 in AX plus CX. A is maximal monotone and C is co-coercive. So that's the problem that we consider throughout. So let us introduce the nonlinear forward-backward map. So for this, we need some operator m, it's single valued, and we assume that it's maximally monotone. And then the forward-backward map is defined like this. And you recognize this from a standard forward-backward step, where we just essentially plug in m instead of identity modulo step size. And if we don't have a co-cursive term, it reduces to this, and this is what we call the nonlinear resolvent. And the m operator here is we call it a kernel. And we have some special cases. So if m is gamma inverse ID, identity operator, we plug that in here. We get this, and then we can just take out the gamma to get this update or this mapping. So it's a forward-backward step. If we instead have gamma inverse times p, where p is some operator, bounded linear self-adjoint strongly positive operator, which we have this shorthand for, we get the preconditioned version of forward-backward splitting. And if m is the gradient of some convex function, differentiable convex function, we get the Bregman forward-backward step. We will not talk more about Bregman forward-backward steps from here on, but this is also a similar update scheme at least. All right, so now let's talk about convergence of this mapping. So what happens if we try to iterate the mapping like this? It is a natural candidate to try to solve this problem, because if we find a fixed point of this mapping, we find a solution to the problem, because the fixed point set equals to the solution set under very general assumptions on m. But it may be that it does not converge this iteration if we assume, for instance, m strongly monotone and Lipschitz continuous. So even in the linear case, this means that the operator m is strongly positive and bounded, but it lacks self-adjointness. So if it's also self-adjoint, some kind of symmetry, it will converge if m is chosen large enough, let's say. But as soon as we lose the self-adjointness, we need to do something else in order to have convergence. So let's show a counterexample for this where it does not converge, the iteration that I just showed you. So in the problem, which was this, this should be in this. We assume that C is 0, and that the operator A is skew symmetric and monotone. Essentially, it's given by this, and it's essentially just a 2D operator, which is a 90-degree rotation, and it's monotone, so it satisfies the assumptions we have on, it's maximally monotone, so it satisfies the assumptions we have on A. And we select our kernel to be gamma inverse ID minus A, and we have gamma to be positive. And this is a bounded linear strongly positive operator, but it's not self-adjoint, so we lose the self-adjointness in this operator. And if we then follow the iteration that we had on the previous slide, we write it out like this, and these two A's, they cancel, and it becomes just a forward step in A, which is given by that. And this is a rotation with a gain that is greater than 1. So it will spiral outwards and does not converge. So the conclusion is that we need some type of correction to use this nonlinear forward-backward map in an algorithm. All right, so one thing we can see about the forward-backward map is that it creates a separating hyperplane between the current point that we are at and the solution set. And this holds under the assumption that A is maximally monotone, C is co-cursive with constant 1 over L, with respect to some P, strongly positive self-adjoint linear bounded P. And we also assume that L is between 0 and 4. And that is essentially because we don't have an explicit step size in the algorithm. But this is no restriction because we can select P arbitrarily. But we also have the additional requirement that the M, the kernel M, should be strongly monotone, one strongly monotone with respect to P. And if these things hold, we can define a function psi x for every x in the space. And if we let x hat be the result of this nonlinear forward-backward step, we define this affine function like this. So it involves x and it involves the result of the forward-backward step. And we have the P here, and we have the coercivity parameter L here, with inverse coercivity parameter. Then it's quite easy to show that, first of all, for all solutions Z, if we plug that in, the output is less than or equal to 0. If we plug in the point x itself, so this, depends on x. So if we plug in the point x itself, this is greater than or equal to 1 minus L over 4 times some type of residual for the forward-backward step. And for all points that are not solutions, and since L is between 0 and 4, this is greater than 0 for all such x. So what we can conclude from this is that we can construct a hyperplane. Okay, let me take the next. We can construct a hyperplane or even a half space according to this, with the help of the output of the forward-backward map. So we need this x hat to define this half space. And what we show then is that the 0 set or the solution set is contained in this half space, and x is not contained in the half space. So a natural thing then, since we know it creates a separating hyperplane, is to project onto it. So the algorithm with projection correction, first algorithm, is to take this nonlinear forward-backward step. Then we construct the half space that contains the solution set but does not contain x, and then we project onto it, where this is the projection onto the space, onto the half space in some metric S. So we use some S norm in the projection. So if MK, except for what we assumed on the previous slide, is also Lipschitz continuous, and these P and S are bounded linear self-adjoint strongly positive operators, and so on, and we also have a relaxation parameter between 0 and 2, then this algorithm converges to a solution of A plus C, 0 in A plus C. But what we can note here from this algorithm is that we need to apply MK twice. So we apply MK at XK to get the forward-backward step, but we also need to apply MK at X hat K, so the result of this, to evaluate or to construct this half space that we want to project onto. So in general, we need to evaluate MK twice in every iteration. And this, depending on what MK is, this could have a substantial extra cost, this second application of M. And we will get back to that when we do a momentum correction. So this is a more explicit version of the algorithm that we just saw. So if we write out the projection, we get an update like this. And this mu k parameter comes from the projection, and it's bounded away from 0. Epsilon should be greater than 0 here as well. And then we can see this update that we have here. So if MK is linear, we can write it like this. And then so this comes up from the projection. So the projection kind of reduces to computing S inverse MK. We're solving that linear system. And as a variation of this, we can replace this mu k that we have by any mu hat k, which is still bounded away from 0, but less than mu k. So that will also converge and it's essentially the same algorithm, but we have a smaller relaxation parameter and shorter steps. So that's one variation that we will get back to when looking at the forward, backward, forward method. All right, so before we proceed, we will just look at the forward, backward splitting method and see that this is a special case of what we just presented. So if we select our MK to be gamma K inverse, which will be a step size, times some strongly positive self-adjoint M, and the P that we had in the algorithm also, select this at M, and also the projection metric S is M, and we assume that our co-coercive term is 1 over beta co-coercive with respect to M and P. Then we can show that we always have this value of UK, and we can define a lambda K like this. And by doing so, we get this algorithm, which is exactly a relaxed precondition for backward splitting method with relaxation parameter lambda. And what we see is that the second evaluation of M, since M, S inverse M, or S inverse MK, equals gamma K inverse identity, this is very cheap. So in a sense, the projection correction becomes redundant, because the projection essentially amounts to evaluating this or solving this, but this becomes redundant, and we get back to the nominal case without projection correction when it's not needed. So one way to view this is that the algorithm only has projection correction. It kicks in if it's needed. If not, it just reduces to the standard forward backward splitting. And we can also see that, so this is just the same algorithm again. We can show that the algorithm actually converges with these step sizes. So we can go up to 4 over beta. And this is not a new result. It's also available in some other papers, but it also comes from our analysis. And the theta that we have, which is used to define the relaxation parameter lambda, is between 0 and 2. So this means that we can allow for a step size gamma, which is greater than the usual 2 over beta, but it comes at the expense of lambda K having to be less than 1. So if we do under relaxation, we can have a bigger gamma K. And in the usual range, we can use lambda K equals 1, so no relaxation, but also over relaxation if needed or if desired. So since forward backward splitting is a special case of no FOB, it has Chambot-Poc, Buchan, Douglas, Ratchford, AGMM with dual step size 1, and proximal gradient method as special cases. But it also has other algorithms. So Zeng's forward backward forward splitting is a special case where M is nonlinear. The Solodov and Zeng method is also a special case where M is nonlinear. The synchronous projective splitting is a special case with M linear, but not self-adjoint. It's strongly positive and bounded, but not self-adjoint. The same thing holds for the Briseno-Arias-Combets method and the primal dual methods by He and Juan. And then we can look at if we have a nonlinear forward-backward step. So in these, we have also a co-coercive operator that were absent from the ones in the list above. Then we have forward-backward half-forward splitting, which adds a co-coercive term to that method, Zeng's method. We have asymmetric forward-backward adjoint splitting, AFPA, where M is not self-adjoint, but linear. And we also have the proximal iterating predictor corrector method, for instance, which is an instance of AFPA. Based on this, we can, if we want, add a co-coercive term to the models of these and incorporate this into the algorithms based on the framework that we just had. And we will see, I have slides later on for a few of these special cases, if you, and some of these we will go into detail on how to arrive at those. All right, but now let's come back to the drawback of the projection correction. And in general, we need 2 evaluations of MK in every iteration in order to run this algorithm. And the exception that we saw was if we do standard forward backward splitting, this evaluation was made simple. It's just a scalar times identity. And in that case, we do not need a second application of MK. This becomes redundant or is not needed anymore. But in most other cases, let's say all other cases, we need 2 evaluations of MK. So how can we avoid that? So this is at least one attempt to avoid that, and we will see often it can be avoided when we, instead of doing projection correction, use momentum correction. So we consider the same problem. We want to find X in the real Hilbert space H, such that 0 is in AX plus C, and A is maximally monotone, and C is 1 over L co-cursive with respect to some S in this set. So the algorithm that we look at now, so this is a different algorithm. It is still based on the nonlinear forward-backward step. So you see, if U is 0, we get back the nonlinear forward-backward step. But the correction in this case comes from the U, and this is a momentum in this operator. So we apply this operator to xk and to xk minus 1 and put it here. And this turns out to be sufficient to guarantee convergence of this full scheme. And again, MK can be nonlinear, but S is linear and strongly positive and so on. So the momentum term is in this operator. So what are the, so let's look at the evaluations of MK. So one motivation for this is to reduce the number of such evaluations. But if we look at the algorithm, in general, we need to evaluate MK minus 1 at xk and MK at xk, which obviously also means that we need to evaluate MK minus 1 at xk minus 1. So in general, we don't save anything here, but if we have a simple relationship between these such that they differ by a scalar, we save one evaluation, which means that we only need one MK evaluation per iteration. And another instance, which is more common, is this, that MK is alpha K inverse ID minus some nonlinear operator D. And then we save one D evaluation per iteration, and we only need to apply it once. So in those two cases, we will save something compared to if we do projection correction. So now let's look at what are the restrictions on M. The algorithm is again here. It's the same algorithm. And if we first try to go to the forward-backward setting, we said MK is gamma K inverse times S. So which means that MK is a strongly positive operator self-adjoint. And it means that this term is 0. Of course, this operator is 0. And U becomes 0. So this term goes away. And we get standard forward-backward splitting. So this is a special case, and it converges under nominal parameter requirements. But we can also allow MK to deviate from this to get other algorithms. And we assume, sorry. So what we assume in our analysis is that this term, that we do momentum correction on, is LK Lipschitz continuous with respect to this S operator. And if this is the case, we can show weak convergence under this assumption. So 1 minus this Lipschitz constant in 2 consecutive steps, and then a term that has the step size and the co-cursivity parameter in it, it should be positive, strictly positive. Okay, and why is that? So the convergence analysis we have for this method is the following. So we define, and we take any point in the solution set, and we define Vk, which we call our Lyapunov function. So this is the distance from this point, which has the sk and some s inverse times the momentum term uk, the distance of that to the solution set plus some residual term that is norm xk minus 1. So if lk is less than 1, we can show that this Lyapunov function at k plus 1 minus lk minus the value at k, and then we have this term on top of that. And if this coefficient here is greater than epsilon, this is exactly the condition that we have here, then we know that this is a proper Lyapunov function, meaning that it decreases from one iteration to the next. And we can conclude that this term is summable. And from these two, we can draw the usual, we can use the usual convergence arguments to show weak convergence of to a solution. So this is the condition. So let's just mention what special cases we have for this. So if we do nonlinear resolvent, meaning C equals 0 in the problem formulation, we get the first method by Malitsky-Tam in their paper, which is called forward reflected backward as well, uses a nonlinear M. We can also arrive at the forward reflected Douglas-Radford method by Ryu and Wu. We might see an example of that later. And then we can add a co-coercive term, and then we get the three operator splitting method that is later on in the Malitsky-Tam paper as well. And of course, we can add co-coercive terms to these methods. And for the first one, it's already done. But in the second one, we believe it's something new. And of course, all these methods have projection correction. And we could, if we want, replace the projection correction by momentum correction. But then we will get new and more restrictive parameter requirements than in the nominal setting. And if we do it for this method, we get the method by Malitsky-Tam. Okay. So before I go into special cases, I will also mention something about Polyak momentum. So the momentum method that we have can actually equivalently be written with an explicit Polyak momentum term, where we assume that theta is less than 1. So if you recognize this method, if we remove that part, it's exactly the same as the momentum method that we had before. But with this part, it looks like a Polyak momentum variation. And actually, it's equivalent to the original momentum algorithm. If we let the step size and u in that method be equipped with a hat, then we have this relationship between the new u and old nu, and new gamma and old gamma. And then we can write it in Polyak momentum form. And if we translate the convergence conditions to this form, we get this as a convergence condition. So which means that we can essentially always add a Polyak momentum term, at least either it's a momentum or it's just an interpretation as a momentum, to all the special cases that we had before. And in particular, I wanted to look at forward-backward splitting. And I repeat the general convergence condition here. And to get the forward-backward splitting, we know that we should choose mk to be this, which means that this Lipschitz constant that we had before is 0. And then we assume that C is 1 over beta co-coercive with respect to S. So B beta equals L in this condition here. So the requirements we have on the Polyak momentum parameter are these. It should be in this range. So for instance, if we have a common step size, which is 1 over beta, then the Polyak momentum parameter should be between -1/2 and 1 over 6. And if C equals 0, so we get the resolvent method, we need a momentum term which is between -1 and 1/3. So we allow for negative momentum in these methods, actually more negative momentum than positive momentum, which may be interesting. All right, so this is essentially a summary of the framework that I presented so far. So we have presented this no-fork framework with either projection or momentum correction. And we have seen that there are lots of special cases to this method, although I haven't provided any details. And with this framework, we can add a co-coercive term to those that do not have it already. We can, in some cases, avoid one application of this MK by using momentum correction instead of projection correction. We can add, or at least interpret, methods to have Polyak momentum to methods that don't have. And it's also quite easy to design and prove convergence of new methods. And this is what we will see next. So the final things I have, the last 10 minutes or so, I have special cases and some new algorithms. And this is a list of special cases that I have added in the slides. I will not have time to go through all of these. But if you have questions on some of these, I have some more details at least in these slides, so we can look at those if you want. So the first thing I have is forward-backward half-forward splitting and Malitsky-Tamm to see how we can arrive at that. Then I have Soledov and Zeng, but that one I will skip. And there is a novel four-operator splitting method that has AFPA as a special case. And this also gives rise to two novel four-operator splitting primal dual methods, one with projection correction, one with momentum correction. We also have another four-operator splitting primal dual method that uses a different kernel than what is used here, which we also believe is new. And then we can extend all of this to multi-operator setting, which we haven't done in the examples before. And one example of that is synchronous projective splitting, which is also falls within this framework. All right, so let me start with forward, backward, forward, and Malitsky-Tamm methods. So in those, we consider monotone inclusion problems of this form, and we assume that B plus D is maximal monotone. We can assume it individually, but it's enough to assume that the sum is maximal monotone. And then we assume that D is delta Lipschitz continuous. And the traditional method, or the method by forward-backward splitting method by Zeng, one of the versions at least, is given by this iteration. And we see that we need a second application of D at X hat. If we instead go to the nice method by Malitsky and Tamm, it has a similar format, and we write it on this form with a UK here. And we see that we need to apply D twice, but we can reuse the second application in the next iteration. So we avoid or rather, we can reuse, we don't avoid two applications of D, but we can reuse one computation. So we only need to compute one of them in every iteration. So this is one iteration can be performed with less computational cost than for forward-backward splitting, forward-backward-forward splitting. All right, so how do we arrive at these? So the first step is to look at the forward-backward map. So how we pose it in our framework is to set A equals B plus D. And this is why we assume that B plus D is maximally monotone, because we only need A to be maximally monotone. And we have no co-coercive term. And then we set our nonlinear operator kernel to be gamma K inverse ID minus D. And we evaluate this nonlinear resolvent with MK and A. We just plug it in to have this as MK, this is A, and here we get, again, have MK. And these two cancel, so we get this. And then we can just take out the gamma K's to write it on this more usual form. So we see that the nonlinear resolvent, MK resolvent in A, is a forward-backward step in B and D. So this is how we go from the nonlinear forward-backward step to a standard forward-backward step. And if we do projection correction and select projection metric ID, we have a step size which is between 0 and 1 over the Lipschitz constant. We choose a conservative U hat K. We saw the mu hat K in the NoFob algorithm, and if we take this conservative, we can a priori guarantee that this will always hold. since mk is 1 over this gamma k inverse delta plus delta co-cursive. And so this gives a conservative step compared to the no-fob thing. And then we have a relaxation parameter, which is given by this, which is between 1 and 2, so over relaxation. And then we get exactly the FBF method, and the convergence conditions essentially agree. But if we instead do momentum correction and take S to be identity again, we get the Malitsky-Tamm, and this is the term we do momentum correction on. So we need a Lipschitz constant of that for our convergence condition. This term is gamma k times d. So the Lipschitz constant is gamma k times delta. And the convergence condition is this thing here. So, and one way to satisfy this is to select gamma k in this range, which is exactly the condition that we have in Malitsky-Tamm. So the conditions agree and the algorithms agree. So of course we can extend this with a co-coercive term, which is already done. We get forward, backward, half forward if we have projection correction, and we get the 3 operator splitting method in Malitsky-Tamm paper if we have more momentum correction. And we can also do Polyak momentum extension, which is also available in the Malitsky-Tamm paper. Okay, so the Solodov thing I will skip. I will just briefly mention this novel 4 operator splitting method. So we can solve monotone occlusion problems like this, which is an extension of the forward-backward forward problem formulation. We have B plus D maximally monotone, D Lipschitz continuous. We add a co-cursive term C, which we now can handle. And then we also have a linear skew adjoint K. And to put this in our framework, we let A take everything. We take B plus D plus K, and then we just keep the C as it is. And the kernel that we use, we take some Q, K operator, and then we just subtract the D and the K, and we evaluate the forward-backward map on A and C in the nonlinear with the nonlinear kernel MK, becomes a backward step in B and then forward steps in the other operators. And then we can use projection or momentum correction in this framework. And one special case is AFBA. If we let D equals 0 and QK equals P and projection correction, we get AFBA. And AFBA has shown in their paper that these 3 are special cases of that method. So I will not go into those details. We can also go to primal dual framework. We can look at problems on this form. B1 and B2 are maximally monotone. Here we have E is maximal monotone and delta Lipschitz continuous. F is co-coercive and V is linear and bounded. And then we can write this problem on the same format as the previous problem when we define the operators B, D, K, and C like this. So these have the properties that we had before, and in particular, we get the skew linear property of K, which we usually have in primal dual formulations like this. And we can specify a specific kernel, MK, which essentially, again, just subtracts the K and D. It's the same kernel, but we select QK in a particular way, where the tau and the sigmas will be step sizes, and lambda K can be chosen differently to get different algorithms. And if we plug that in to get, if we evaluate this nonlinear forward-backward map, the update equation is like this. And you recognize, for instance, if lambda K is 2 and F and E and F are 0 and E is 0 at least, we get Konrad-Wu, and if F is also 0, we get Chambopok. If MK, but in general, this MK is not linear, positive, strongly positive, and so on. So in general, we need correction. So we can do projection correction, and then we get an algorithm that looks like this. We will not go into the details. We have a convergence condition like that. And we need two evaluations of V and V star, unless we select lambda to be 1, and two evaluations of E. And for the other ones, we have one operator. And interesting is that this primal dual method does not give condat rho when reduced to that setting, because of the S that we have chosen, this S. This is a convergence proof. So this is everything we need to prove convergence of that method, but I will not go into it. And then we have a primal dual method with momentum correction. We select this S and MK, and then we get another algorithm that looks like this. And this extends, for instance, the Malitsky-Tamm 3-operator splitting method, and it extends the forward reflected Douglas-Rutherford method by Ryu and Wu, and also the condat-Wu method. And all resolvents, forward steps, and V and V star operators are evaluated once. Here we have convergence. And the final thing I want to show is that we can have a different kernel, MK, that we evaluate, that we define like this. And this MK actually involves a kernel inside of MK. So the nonlinear part is, a resolvent of B2 inverse in MK. And the algorithm looks like this. Everything is evaluated once, except for the resolvent of B2, which is evaluated once. And this method seems to be new to us, at least, in the requirement of two B2 operators. But if the B2 is 0 and V is 0, we get the Malitsky-Tamm 3-operator splitting method. So it's in a sense an extension of that. And the convergence conditions are these, and they reduce to the Malitsky-Tamm conditions if V is 0. Okay, so I already had the summary of the framework before. And with that, I would like to thank you. And these are the two papers that the talk is based on. Thank you.
Thank you very much for an interesting talk. Are there any questions? I have a question, Pontus, the first question. So actually everything starts with this method where there is also projection on a hyperplane, I guess, or is it a half space? A half space, I guess, yes?
Yes.
So, and then this is then, or this brings me to the following question. So could one make instead two projections in the sense of the Hogazo algorithm to get something which is then strongly convergent? Like to construct another like hyperplane and then with a corresponding half space.
Yeah. So essentially, I don't think that Hogazo's method would be covered by that, but essentially we can replace this HK by anything that is inside. If you just add a second, if we have this hyperplane or half space and we add another one in intersection, then we can project onto the intersection and we still have the same convergence result. But it will not, I don't think maybe that Hogazo's method will be a special case of that, and for sure we will not arrive at strong convergence just by doing this, but at least it's algorithmically a possibility.
Okay. I think Radu was saying maybe if you extend your your thing, then to have two projections in the projection case, then you could get strong convergence.
It might be. We haven't looked into that at all, so it might be the case, but I don't have a good answer to that.
The idea would be to consider another half space and then to make another projection, and then like with the aim to get strong convergence. See, this is what Hogazo is providing.
Yeah.
Yeah. Yeah, I think
But-
it's
but
definitely
I think-
possible.
Yeah, but combining that with this twisted kernel doesn't seem obvious.
Yes, it is not obvious. Yes, but okay.
Yeah, it might be worth looking into.
Jonathan?
Yeah, so if you want to, extend your empire to the entire galaxy,
Mhm.
then the issue becomes, what about inexact computation?
Yeah. We haven't addressed that at all in exact computations.
Yeah. So I have a fundamental question. So there are two papers by Soledov and Spider just on inexact proximal point, right? One that has a projection correction and one that has like this extra gradient correction. Is that related to this, your two correction possibilities?
Probably. Yeah, I guess this is probably the only way to construct a separate, maybe not the only way, but to construct a separating hyperplane in this setting. And I think, I mean, inexact computations, as long as they behave nicely towards the end, I think it would be quite straightforward to include them in the analysis as well.
Yeah, you just get another layer of complexity, of course, right?
Yeah, you probably get some other term in the Lyapunov analysis, and you need for that one to be summable, probably. And if you would be happy to assume that, then I think it would be quite straightforward to introduce at least some approximations.
Well, I guess there's also the whole relative error world.
Yeah.
So you haven't, okay, interesting. And I had a question about the last few slides, which you took away, which was like, so in the case of synchronous projective splitting, you can independently choose all these proximal parameters and so forth. And I wasn't sure how to jam that into your framework.
Yeah, so I can find these slides. So essentially, I do just the full, not block updates and no asynchronous or anything, just synchronous full updates, and consider this simplified problem. And then we do the primal dual reformulation into some monotone plus skew operator. And this, for instance, fits in the 4-operator splitting framework with no co-cursor term and no Lipschitz term. So if we, and of course, solutions to this problem, then the X part is if and only if it's a solution to the original problem. So then, yeah, this is how it usually looks, but you can also write it like this. So if you write MK to be some strongly positive linear bounded operator P, and then you subtract the K, and then you let A be B plus K, and you don't have a co-cursive term. Then when you do in this case, it's not nonlinear, but it's skew, it's not self-adjoint. If you do this update, you will get that thing where these two K cancel, and this is the update. And this is exactly the thing I had on the previous slide, which is synchronous projective splitting.
Okay,
and so the step sizes come from,
So M depends on K. That's how you can get all this freedom in choosing the prox parameters, right?
Yeah. And then the condition we have essentially is that this is Lipschitz continuous, and this is for sure. And as long as we bound these step sizes, this is also true. We can also have iteration dependent, and we also have strong monotonicity. But since this is skew-symmetric, it doesn't add to strong monotonicity. So we only need for this to be strongly monotone. And since we only have these diagonal entries, the only thing we need are that these diagonal entries are positive and bounded. We could also add iteration index to them if we want. So that's where the the no step size restriction comes from.
Yeah, just okay. Thank you.
Thank you.
Thank you for a question.
Minboy.
I just want to comment.
We cannot hear you. Could you please fix your microphone?
Can you hear me now?
Yes.
So I just want to comment on Professor Bott's question ago, right? Because this method from Pontus is a phasor monotone method, right? So any phasor monotone method, we know that if you add another half space in there to get strong conversion for free from Agazol, right? Because Pontus, because in the end you have a phasor, you're proved by some phasor monotone principle, right? And
yeah, the method is based on the first method is based on phasor monotonicity.
Right.
That's correct. The second is not.
Yeah, but for the first one, if we have a cutting plane to separate the zero and the point, then we know that we can always add another cut in there from Professor Comeback 2001 paper, and then you get strong conversion for free. Right? Prove exactly the same.
Yeah,
if the Wing to strong conversion principle by Bowsker and come back in 2003.
Yes, but then the question is how to, I mean, just formulate the second hyperplane in a meaningful way. And
that step is explicit, right? You will get a closed form formula for the second step.
Yes.
Yeah.
Okay. Yes. So there is a possible adaptation of the algorithm just to get strong convergence. So we have a question in the chat. So asked by Stefan. Do you like to ask the question or should I read your message? I can also read it. Okay. So Stefan is asking, are there any speed of convergence results for this general nonlinear operator splitting framework? And if so, are there any step size rules to maximize convergence speed?
The thing that we have is a linear convergence result in if we assume a metric subregularity of A plus C. And then we have a linear convergence result for the sequence, or linear convergence to a solution for the sequence.
I mean, for the general method, yes.
Yeah, so no, yeah, we have it for the projection correction method, but we don't have it for the other one. We believe it holds still, but we haven't included it in a paper. But the linear convergence result is in the projection correction paper under metric subregularity assumption.
Okay.
And I think that the coefficient that we get out of it, first of all, it depends on the metric subregularity constant, which is maybe difficult to estimate. And then there are probably also a few other, let's say, conservative steps in between. So I think to optimize it with respect to the step size would not be very useful in practice anyway. So we didn't do that step.
Okay. Thank you. Are there other questions? So I will have a further question. So I mean, you show that you are able to cover with your method many algorithms in the literature, but you also proposed new algorithms. So do you have any idea, are these new methods of some use? I mean, do they behave well in regular experiments, or do you have any comparisons?
No, we don't have anything at the moment. So what we are focused on so far is the let's say the algorithmic the general algorithmic idea to say that this is very encompassing, let's say, and we have not focused at all on which algorithms that perform better. But my intuition is, at least, the closer we are to a symmetric kernel, let's say, the better it performs.
Okay.
That would be one intuition. And apart from that, yeah, I can't say much, I would say.
Okay. Matthias, do you have a question?
I'm not sure if it's really a question, it's more speculating. So with the negative momentum that you are able to introduce in some of the schemes you presented, what conceptually do you believe would it help you? Would it help you to decrease or to relax some assumptions you impose on the operators, like the co-cursivity? Or would you believe that you get a wider range of convergence radii for the iterates? Maybe you can give me some intuition for that, for the negative momentum. I was not sure to completely follow this part.
Yeah, so this one, right?
Yes.
Yeah, so we were also a bit surprised about that, because we typically don't see negative momentum. But at the same time, and it's interesting that it's more negative momentum than positive momentum, but at the same time, we don't think it would improve.
Okay.
Convergence.
So there's nothing.
It allows for it. It doesn't. So our intuition is that it doesn't push. Let's say it doesn't push forward the iteration, but it's essentially a defensive strategy to pull you back towards the previous point. And it turns out that you may allow for that to do that even more, because it's defensive. You just pull it back. But in terms of improving convergence, I would suspect that it's not beneficial to have a negative momentum. But again, we didn't even test that. But that one we shouldn't have tested. We should have tested probably,
so
because it's not very difficult.
There is a set of papers in a machine learning context by Gidel. I didn't check for correctness of these results, but they advocate the use of negative momentum in some extra gradient kind of schemes.
Okay.
I'm not sure that they have a lot of rigorous results here, but I remember that there was a discussion at some of the NeurIPS papers a couple of years ago, and they advocate as well the negative momentum heavily in some applications. You can guess around GANs, of course.
Yes.
And that's why I was speculating just the negative momentum, whether you see any room for improvement using negative momentum, or saying it more concretely. If I give you an inclusion, can you tell me, okay, to this problem apply negative momentum, to that problem apply a standard positive momentum? That would be my high-level question. I'm not even sure that this is a question, as I said.
Yeah. And for that, we can't do that. I would say not at the moment. That would be difficult. But what I can say at least is that the negative momentum comes from this in the convergence condition. But one of them is with absolute value, and the other one is not with an absolute value. And this also gives typically bigger negative momentum than positive momentum. And this comes from the assumption that theta less than 1, that one of them does have an absolute value and the other one does not.
Interesting.
Yeah, and I think if you look at this condition, it is not only for the forward-backward splitting itself that we can have negative momentum, but it's also for more general L, right. So for forward-backward forward type methods and so on.
Interesting. Thanks.
Thank you.
Thank you, Matthias. Then, okay, actually having a discrete scheme, of course, the natural question would be, if there is an interesting continuous time approach. Okay, I wouldn't ask this question, but what I like, I mean, I will ask it. Why? Since I like this the momentum correction term, which when in continuous time corresponds just to the time derivative of, let's say, the operator at xt. So and then I guess that in combination with such terms, then I get that the continuous time scheme is very interesting.
Yeah, that's That's a good idea. We didn't at all look at the continuous time, but yeah, that's a natural thing to say that it comes from.
Yeah.
And then a discretization of that would give this type of correction.
And I like this type of constructions. Of course, they appear also. I mean, Octa is related to this construction, but they are of great help when investigating monoton and Lipschitz operators.
Yeah.
Okay, but
yeah, that's a good point. We should probably try to see what type of continuous time dynamics that would give rise, and discretization that would give rise to this.
Yes.
To see if that could tell us something as well.
Yes.
That's a good comment.
Okay, great. Other questions? Oh, then Pontus, thank you very much for a great talk. So we had also a great discussion.
Yeah, thank you very much.
So it was a lot of fun. So we will post the video and the slides on our website. And I'd just like to announce that our next speaker will be Giovanni Nunes Grappiglia from Leuven. Next Monday, same time. I wish you a nice week and a great afternoon. Thank you, Pontus.
Thank you. Bye-bye.
Bye-bye.